Hi, this is David Follis, and this is our continuation of our video series on why WebSphere Application Server on zOS. The argument for WAS on zOS is built upon the premise of zOS. That's why we say that the why WAS on zOS question is ultimately answered with because of zOS. The value argument for WAS zOS would be very difficult to make without the value of zOS being established. That's what this section is about. It provides a review of the attributes of systemz and zOS. The hardware on which zOS runs is systemz. That hardware has a history of being built around two essential design philosophies, reliability and throughput. Both design philosophies are related to the role of systemz running core business functions. Without going into all the details of the systemz hardware design, there are many publications that provide that information, the key here is to note that the systemz hardware architecture is based on redundancy and non-disruptive updates. Throughput is achieved with very fast processor clock speeds, coupled with a balanced cache and memory and I/O subsystems designed to match. Later on in this presentation, the topic of high availability will be covered. The very first principle of a highly available architecture is to avoid an outage in the first place. The outage that does not occur is the outage that does not need to be recovered from. Systemz is the hardware platform at the bottom of the WAS on zOS architecture stack, goes a very long way towards the goal of avoiding hardware outages. The design of the hardware, with its multiple points of redundancy, minimizes disruptive outages. For more on the systemz EC12, see the Red Book IBM Z Enterprise EC12 Technical Introduction. PRISM, an acronym for Processor Resource Systems Manager, is a Type 1 hypervisor that allows multiple logical partitions to operate on a physical systemz hardware server. PRISM is supplied as part of the systemz hardware microcode function. The ability to partition the physical server into logical partitions is the first step in providing redundancy of the operating system for a highly available design. Each logical partition, or LPAR, is separate from others. Outages at the OS level in one LPAR do not affect other LPARs. Another step in the HA story is to then cluster the LPARs for shared application and shared data. On systemz and zOS, that clustering is called parallel sysplex. We cover that a bit later in the presentation. Though running on the same hardware, the degree of separation of the LPARs is enough to earn the EAL5+ security rating. That allows flexibility to partition particularly sensitive workloads from other workloads. Several different operating systems may run within the LPARs. The one we'll focus on in this presentation is zOS. We'll touch on Linux for systemz later. The server resources allocated to the LPARs is adjustable, either manually through the hardware console or autonomically by elements of the zOS operating system running in the LPAR. Those elements are Workload Manager, WLM, and Intelligent Resource Directory, IRD, which we'll cover later in this section. Systemz specialty engines provide a place where certain classes of work may be offloaded. The benefit of this is twofold. First, it leaves more general processor or GP capacity for traditional workloads. Secondly, the work that runs on the specialty engines falls outside software licensing accounting based on GP usage. This makes the financial profile of running these offloadable work classes more attractive. The chart shows the various specialty engines and provides an indication of what they're used for. For WAS on zOS, the focal point is the ZAP engine, which is used to offload Java workloads. Java is at the heart of WAS for zOS, and 50 to 80% of WAS zOS cycles are eligible for offload to ZAP engines. Note that the percentage of offload is a function of the WAS zOS configuration and the nature of the applications running in WAS on zOS. For example, an application that performs intensive computation within the JVM would imply a higher percentage of offload. Remember that Java offload to the ZAP is completely transparent to the Java applications running in WAS on zOS. ZAP on zip is essentially the same thing as ZAPs, except that it allows both Java work and zip-eligible work to be performed on the zip. That's simply a way to more efficiently use a pool of specialty zips rather than having to allocate processors as ZAP or zip. The next layer up from the hardware and the partitioning technology is the zOS operating system. As noted earlier, zOS is not the only OS that runs on the systemz hardware, but for the purposes of the WAS zOS discussion, it's the one we'll focus on. Later we'll touch on Linux for systemz and the role WAS for Linux plays there. Like the systemz hardware, the design philosophy for the zOS operating system has its roots in resiliency. The text in the highlighted box on the chart comes from a recently retired IBMer who was involved in the early days of zOS design and development. The key message in those words is that zOS was and is designed to withstand faults that might otherwise take down an instance of an operating system. Another element that's often overlooked is the fact that zOS is designed to run on System Z hardware. zOS is not designed to be a platform-neutral OS. It's very platform-aware, and the platform on which it is optimized to run is System Z. There's a great deal of low-level integration between the OS and the hardware. zOS is designed to be a multi-tenant shared workload environment. That allows more efficient use of server resource because workloads of mixed nature may be combined on zOS, with zOS enforcing memory separation through its storage virtualization technology. On top of that, zOS has a rich set of management and monitoring tools that allow you to get a very good handle on what's going on within the system. We'll see WLM, RMF, and SMF come up later in this presentation. The purpose of this chart is to emphasize the nature of zOS as a mature, stable, and reliable operating system, while also keeping an eye on the ability of zOS to run newer workloads, like Java. Stable and mature does not imply old and limited. It means zOS has gone through considerable real-world usage, and its proven nature is, well, proven. There is no question that younger people in the IT industry do not have as much enthusiasm for the zOS green screen interface as do those who've worked with zOS for a long time. The need to have a more modern, graphical administrative interface to zOS is well understood, and to that end, the zOS Management Facility provides it. zOSMF is a Java-based application which runs within an embedded copy of WAS-zOS that provides a graphical interface to the administrator, with lower-level hooks to the zOS operating system. The traditional green screen interface still exists for those administrators skilled in that area, with zOSMF providing the graphical interface for newer administrators. There's a tendency at times to think of zOS as being what it was 10 or 20 years ago, but that's simply not true. There have been considerable updates to zOS in the recent past to include newer technologies and workloads. For example, we often find some are surprised to learn zOS supports Telnet and SSH. zOSMF is really part of the same general trend. Maintain the core reliability and high throughput attributes of zOS while adding newer technologies and newer interfaces over time. zOSMF is a means of updating the administrative interface of zOS to make it more approachable and usable by newer staff. As noted earlier, zOS is a shared environment operating system. zOS maintains logical separation of tasks and maintains a very strong separation of virtual memory, so one process can't interfere with or harm others. Part of the design of zOS allows for communication exchanges to occur cross-memory, that is, between the address spaces of two programs wishing to communicate. When cross-memory communications occur, there is no invocation of the TCP/IP stack at all. Typical examples of cross-memory communication include JDBC Type 2 between WAS-zOS and DB2 on zOS, CIX EXCI between WAS-zOS and CIX, MQ bindings mode between WAS-zOS and the MQ manager, and WOLA, which is a function of WAS-zOS that we'll cover in more detail later. The first obvious advantage of cross-memory communication is it provides a very low level of latency. Since there's no network protocol code path to go through, the processing is highly optimized. Reduction of per-transaction latency is particularly important in very high-volume operations, where the additive nature of each transaction's latency can make overall throughput longer. But reduced latency is not the only benefit. The chart outlines other benefits we highlight when discussing cross-memory communications and zOS. The point is that cross-memory communications, or the ability to co-locate WAS-zOS and key data subsystems in the same zOS instance, has many advantages over network-based exchanges. The benefits are cumulative. That is, any one taken by itself may not be compelling, but taken together, the story becomes very compelling. Despite all the claims of the resiliency of the hardware and the zOS operating system, a single instance of that would still be viewed as vulnerable to outage. Therefore, when the topic of high availability is in the background, a discussion of clustering of server instances is necessary. Simply adding more server instances is really the easy part. The often overlooked aspect of that is what to do with data access. Too often we see cases where the application tier is clustered for availability, but all the instances point back to a single instance of a data server. That provides a degree of availability for the application tier, but the data tier remains a single point of failure. Parallel sysplex is a mechanism that allows up to 32 zOS instances to be clustered, Within the heart of Parallel Sysplex is the coupling facility, which provides data structures to be shared between members of the Parallel Sysplex. Communication links between each zOS member of the Sysplex and the coupling facility provide a very fast means of signaling, which is what allows rapid update of locking information on the shared data. Note how the chart shows an instance of each key data middleware component, DB2, CIX, IMS, and MQ, on each zOS instance. Each zOS in the Sysplex has its own instance of the middleware, and those middleware functions are all Sysplex enabled and able to participate in shared data. zOS in any given member of the Sysplex has, local to it, an instance of the data middleware. The middleware instances are not shared. The data is. Parallel Sysplex provides two attributes to zOS: availability and scalability. Duplicated zOS instances with duplicated data middleware instances with duplicated zOS instances running duplicated copies of the application, all running on top of an extremely efficient data sharing model hosted by the coupling facility. Parallel Sysplex has been around for almost 20 years now, and the complexities of scalable data sharing and data locking have been worked out. Others have data clustering technology, but you'll find challenges exist with the scaling. That's the value of Parallel Sysplex. It provides the key clustering foundation under zOS for purposes of availability and horizontal scalability for increased throughput. WLM is a key component of the zOS story because it provides the facility for managing resources to goals. In a shared environment, work tends to organize into levels of relative priority. Some work is of great importance, other work of lesser importance. WLM is the tool on zOS to take as input your defined goals and manage all the work seen on the zOS system according to those goals. WLM is what allows zOS to operate at levels of utilization much higher than other operating systems. WLM's objective is to manage system resources to meet all the defined goals. In some cases, this may mean pushing lower priority work aside temporarily so higher priority work can achieve its goals. Absent a facility like WLM, the tendency is to plan capacity to peak and live with underutilization the rest of the time. With WLM, there's the ability to plan capacity with a higher level of average utilization. The key point to understand here is that WLM plays an extremely important role in the operations of all things on a zOS system. WLM advises other functions, such as TCP, on routing decisions. WLM reports on resource usage, and WLM is Sysplex aware and is capable of advising on dynamic resource allocation between zOS images. WAS on zOS relies on WLM to a considerable degree. How WAS on zOS makes use of WLM will be explored later in the presentation. On the previous chart, we mentioned that WLM is Sysplex aware and capable of participating in the dynamic adjustment of server resources between logical partitions, or LPARs. That function is called Intelligent Resource Director, or IRD for short. There's a considerable degree of integration from the hardware up through the operating system and into facilities of the OS. The hypervisor, called Prism, is a function of the hardware. zOS operates in logical partitions on the server. WLM monitors and manages resource usage within the OS instance. WLM works with IRD to shift resources between LPARs if needed. Now, picture in your mind the data sharing capabilities of Parallel Sysplex and key data systems such as DB2, CIX, IMS, or MQ. Then layer on top of that WAS zOS. The picture that emerges is that of an extremely robust, clustered environment with autonomic function for resource management. System Z in zOS has had the ability to host the TCP/IP network protocol for quite some time. That function has matured to a considerable degree, including supporting IPv6. The TCP/IP stack on zOS includes network optimizations that can help reduce overhead and latency in a high-volume environment. For example, numbered block 1 on the chart refers to a function of TCP on zOS that understands when the source and target of a TCP connection are on the same LPAR. Rather than exercise the full TCP/IP stack all the way down through the lower-level IP routing function, the TP stack processes down through only the necessary code to enable the connection. No IP code is touched. It doesn't need IP when the source and target are in the same LPAR. And the connection is made cross-memory, so no adapter code is exercised and no wires or optical cables are touched. Another networking function of systemz is something called hypersockets, which is a means of mapping an IP network onto a virtual network deployed on the memory backplane of the physical systemz server machine. Again, no adapters are exercised, no wires or fiber optics are employed. Even if hypersockets is not defined, the system is smart enough to understand when the IP call is between LPARs, and it will drive the function down to the system adapter, but not out onto the network wires. When talking about system networking, the subject of virtual IP addresses and sysplex distributor comes up. The ability to define IP addresses separate from the IP addresses of the physical adapter is important for purposes of high availability. If a physical adapter is lost, then the hard IP address of that adapter is lost as well. Hostnames resolve to IP addresses, and if the resolution algorithms in the network are not updated, then client access based on hostname will result in a failure. Virtual IP addresses are abstracted from the IP of the physical adapter, and in the event of an adapter failure, they may be automatically rehosted to a surviving adapter. Hostname resolution mechanisms in the network see no change. Sysplex distributor is a function of zOS TCP that provides intelligent TCP connection placement services based on WLM advice. Imagine a client seeking to connect to a WAS zOS server that's clustered in a parallel sysplex environment. The client can be configured to use a hostname that maps to a virtual IP address. The TCP connection request is handled by sysplex distributor, which, at the time of the request, determines which LPAR is best suited to handle the request. In the event the LPAR on which the sysplex distributor function is being hosted is lost, the surviving TCP stacks in the sysplex will automatically and non-disruptively take over the sysplex distributor function. This dynamic movement may be accomplished with operator commands as well, which is of value in doing planned maintenance. When we get to the section on high availability later in the presentation, we'll see that HA is really a total system approach. It's not just putting additional servers into place. Networking distribution and request routing recovery after failure is a part of that as well. The security infrastructure on zOS is provided through an interface called SAF, Security Access Facility. Behind that interface will be a security product. IBM's product is RACF, Resource Access Control Facility. RACF is far more than just a user ID and password checking mechanism, though it does that as well. RACF provides a mechanism to control access to resources on the system. The access control applies to people who are on the system, application programs that are running on the system, and address spaces that are created as part of overall processing. The strength of security on zOS is well known and has a well-deserved reputation. The reason security is so strong on zOS is twofold. First, the nature of RACF and how it controls access to nearly every resource on the system. And second, the greater ability to put in place and control security governance practices for a consolidated system like zOS. A security system's effectiveness is a direct function of how carefully the administrators of that system perform their role and how effectively the security of the system can be monitored and audited. RACF on zOS has a long history of carefully defined governance procedures, and those governance practices are entrusted to a few security administrators who control a consolidated server environment. Contrast that with an environment where the security components are fragmented across multiple environments and governed by many different people with different levels of security discipline in place. That's not to say that effective security outside of zOS is impossible, because that wouldn't be true. It is to say that the effectiveness of security on zOS is much greater because of the nature of the zOS operating system, the consolidated shared nature of its design, the design of RACF to consider nearly everything a resource to be protected, and the strict security practices that wrap zOS systems based on decades of experience. A key first step to effective capacity planning, performance tuning, and resource chargeback is having a good understanding of what's actually taking place on the system. The way to get a good understanding of what's taking place on a system is to have tools that provide the necessary information. That's the role of SMF and RMF on zOS. SMF, or Systems Management Facility, is a mechanism on zOS that efficiently logs activity information for those components of the system that wish to write SMF records. WLM writes SMF records for system performance. CICS, DB2, and other key data systems write SMF records. RACF writes SMF records for security-related information. SMF captures all this information, first in memory buffers, then the information rolls down to SMF datasets. That becomes the source for data analysis and reporting tools, of which RMF on zOS is one such tool. Other vendors produce tools to evaluate SMF records, and statistical analysis programs are often used for custom SMF record analysis. All that sets the background for WAS zOS, which writes the SMF120 subtype 9 record. The SMF120.9 record was introduced in WAS zOS version 7 in response to customer input on what information they wish to see for WAS zOS. The SMF120.9 record contains key information about each request activity that takes place within WAS on zOS. The value in SMF and RMF is that it provides you meaningful insight into the activity of your zOS system and the key components that run there. That insight, in the form of detailed activity and performance information, is what allows very detailed capacity planning, performance analysis, and activity chargeback to take place on zOS. Those processes become more and more deterministic with detailed information. IBM develops, maintains, and makes available a compliant Java SDK for the zOS platform. It's available in either 31-bit mode or 64-bit mode, and is available at several different specification levels. This chart conveys several important points about Java on zOS. Java and zOS are not exclusive of each other. Java is a platform-neutral language. It's the role of the Java Virtual Machine, or JVM, to perform the necessary platform-specific integration. That's exactly what IBM has done with its Java for zOS implementation. The JVM IBM has developed is entirely its own, and it was developed with IBM's knowledge of operating systems and virtual storage built up over decades of experience. All JVMs are not made equal. The JVM for zOS is very much aware it's running on zOS, and very much aware it's running on System Z hardware. It's the role of the JVM to abstract the platform from the application, but IBM takes it further and has coded the JVM for zOS to take specific advantage of the operating system and the hardware on the server platform itself. These extensions do not change the standard application interface of the given Java specification. They extend it. Java work on zOS is eligible for offload to the ZAP or ZAP-on-Zip specialty engines if available. The dispatching of work to the specialty engine is entirely transparent to the Java application. Application developers are not required to write Java code for zOS. Their Java code may take specific advantage of zOS through the extensions provided if that's desired. Otherwise, Java code is Java code and will run on Java for zOS. The essential message of this section was that System Z, zOS, and Parallel Sysplex provide a considerable list of functions that can be taken advantage of by a higher-level program such as WAS for zOS. Higher-level programs not written to take advantage of these functions still derive benefit from running on System Z, zOS, and Parallel Sysplex. These we will refer to as indirect or passive benefits, and would include the general reliability of the platform. However, programs written to take advantage of specific functions derive even more benefit. WebSphere Application Server for zOS is designed to take direct advantage of the key platform functions of System Z, zOS, and Parallel Sysplex. That's the key value statement of WAS zOS. It leverages the platform functions of zOS. That's why we stated earlier that the why WAS on zOS question is ultimately answered with because of zOS. The next step is to review how WAS on zOS exploits the key functions of the platform.